Good evening to all of you. We are back again with another exciting session. I, Ajay Jha, on behalf of ACS India team, welcome you to today's ACS Science Talks session. Today, we are pleased to have Professor Soumitra Satapathi with us. Professor Satapathi is an associate professor of physics and joint professor of nanotechnology in Indian Institute of Technology, Roorkee. He received his PhD and MS in physics and applied physics from University of Massachusetts, USA. His research group is actively indulged in the fundamental understanding and translational applications of various functional materials using steady state and transient spectroscopy, about which he'll be discussing today. Professor Satpathy is the recipient of various national and international awards. To mention a few, Young Faculty Research Fellowship Award by Ministry of Electronics and Telecommunication, Government of India, the Max Planck Institute Directors Award, Young Scientist Award by Department of Science and Technology, and many more. He also serves as an editorial member at Scientific Journal of International Repute and has written books on photovoltaics and nanophotonics. Now, I would like to invite Professor Satpathy to deliver his talk. Professor Satpathy, please.
Good afternoon, everyone. First, I'd like to thank the ACS India team for giving me an opportunity to share our ongoing research activity in this pressing time. Today, I will talk about advancing perovskite single crystals fundamentals and applications. So my talk is mainly distributed in three different segments. The first, I will discuss about the importance of the energy research in Indian scenario and in the global scenario. And then we'll talk about the perovskite single crystals, mainly the organic inorganic perovskite single crystals, which is made out of the lead-based compound. And then I will discuss about the lead-free perovskite single crystal and some of the very fascinating applications which can originate from this lead-free perovskite single crystal. So many of you probably have read this book from David Goodstein of the Out of Gas. So this book talks about the fact that the way we are utilizing our daily energy, very soon there will be a time when we'll be out of all the sources of the existing energy source. Now, from the morning to the night, we can't imagine a single moment when we can live our life without the use of the energy. So even I am giving this talk and you are listening to this talk, that also is possible because the electricity is there. And it is also possible because there is a steady internet connection is there, which is powered by the electricity. Now, where this electricity is coming from? This electricity is coming from the burning the fossil fuels like coal, natural gas, and all other existing fossil fuel source. But their resources are limited. Very soon, the way we are utilizing it will come to a situations that there will be no source of the conventional energy. And American Petroleum Institute estimates that we'll consume all world's oil within next 40 years. So then what will happen after that? Not only this problem, there is another very serious issue is about the global warming or the environmental pollutions. Because of the continuous use of the conventional energy and also at the same time the global warming, the temperature of this universe and the earth is increasing, and that leads to the melting of the snow in the iceberg and north and south pole. Now, this kind of climatic change needs a very urgent attention, especially to reduce the carbon dioxide output and any kind of carbon emissions so that we can go to more carbonless economy. So there is a very, very urgent need for the energy and also to make a sustainable and renewable energy, not only in Indian scenario, but also in the global prospect. So the story is all about the energy. And as we all agree that whether it is medical industry or whether it's an engineering industry, energy is the blood of the civilization. And it needs a urgent attention of the scientific community to look for how to solve the energy, especially how we can make new materials to grow or how we can develop new materials so that we can become energy independent in our country. So as we all know that the Rome was not built in a single day. So similarly, if we look at the energy revolutions, it was also has passed through several phases. And that was possible by the discovery of new and new materials. For example, initially when the polycrystalline silicon and single crystalline silicon what was at its hem, then the single crystalline silicon solar cells gains lots of popularity. The Bell Labs has successfully used this single crystal and polycrystalline silicon solar cells for making the devices, and furthermore, they have utilized it in the outer space satellite purpose also. But with the discovery of the thin film processing technology, we came across with the amorphous thin film based solar cell, which is often called the second generation solar cell. And with the discovery of the new carbon based engineered nanomaterials, for example, carbon quantum dots, or like two-dimensional materials like graphene and then molysulfide, and also there are materials like carbon nanotubes, metal nanoparticle. They has all led to the discovery of a third generation solar cells. So these are dye sensitized solar cells, then conducting polymer based organic solar cells. And when we combine this new kind of material with all the other existing types of solar cell, either organic or inorganic, then we get a hybrid solar cell, which is often called a fourth generation solar cell. This fourth generation solar cells includes various new types of solar cell. For example, plasmonic solar cells, singlet fission based solar cells, and also a tandem of the organic and silicon and perovskite and silicon tandem solar cells. Now, the major difference between the different generations of the solar cells are that like the cost to the efficiency. As you can see that the first generation silicon solar cells often shows a very high efficiency, but they also come with a very large cost. So since a technology will be viable only if the cost and also the efficiency circle or the triangle is optimized, therefore there is a continuous surge of research of discovering new materials for finding a low cost and high efficiency solar cell devices. Now, in this context, the perovskite has gained a momentum recently during the last 10 years significantly. For example, if you look at this energy evolutions data from the National Renewable Energy in the America, so you can see that starting from only 2010, within last 10 years, the efficiency has reached to 25%, and it is increasing day by day. So this kind of energy revolutions has happened only in a span of 10 years. So not only in the application of the energy, this material has been applied in the case of light emitting diode for making lasers, different kind of photodetectors, imaging probe, and whatnot. So sometimes that's why scientific community call it the wonder material of this century. Now, what is perovskite? The history of the perovskites actually dates back to 1839, when in the Ural Mountains of the Russia, Gustav Rose first discovered the perovskite. And the person who identified its crystal structure was Louis Perovsky. He was a Russian mineralogist, and according to his name, the material called as a perovskite. And this material is found in an abundant quantity in the Earth's mantle. Any material having a crystal structure ABX3, where A is usually an organic or inorganic cation, B is a divalent metal, which has a coordination number of 6, and X is usually an oxide or an halide, for example, chlorine, bromine, iodine. So they are called the perovskite-based material. Now, if this X is an oxide, then it is called an oxide perovskite. For example, this barium titanate or calcium titanate, which have been used for quite a long time as a good ferroelectric material. And if this oxide, in the case of this X, if we replace it by halogen, for example, chlorine, bromine, or iodine, then we call it as a halide perovskite. So now if we look at the crystal structure of the perovskite, so a standard organic, inorganic perovskite crystal structure looks like that, where we have this octohedra, especially this corner sharing octohedra. And when this corner sharing octohedra meets each other, they creates a void at the center, and this kind of cubo-octohedral voids encompass the organic cation. Now, once experimentally somebody has made a perovskite structure, then usually they confirm it whether it is a perovskite structure or not by using the so-called Goldsmith tolerance factor. Now, the Goldsmith tolerance factor by definition is defined by T, which is given by this formula, where the Ra is the radius of the A cation, Rx is the radius of the X halogen, B is the radius of the metal ion, and X is the radius of the halogen radius. Now, usually for a perovskite crystal structure, the T value is between 0.9 or 0.721. For example, if the T value comes out between 0.9 and 1, then it is a cubic structure. Whereas if the T value is between 0.7 and 0.9, it's a tetragonal or orthorhombic crystal structure. But when the T value goes beyond 1, then it leads to a non-perovskite structure or layered perovskite crystal structure. Now, how one can measure this thing? One can measure this either by some theoretical simulation, for example, DFT or any other kind of advanced theoretical simulation, or experimentally from the X-ray diffraction pattern by measuring the lattice parameter and calculating the tolerance factor. So now we are interested to see, this material, they show a very, very peculiar type of electronic properties. This material is an ambipolar charge transport materials where the electrons and hole transport happens inside the same material. And the binding energy of these electrons and hole are much less than the organic materials. So with a very limited amount of the energy, this material can usually at the room temperature dissociate as a free charge carrier and can contribute to the current. The electronic structure originates between the valence band and the conduction band. And here, the lead halide octahedra actually contributes to the origin of the band gap in this kind of material. For example, the s orbital of the metal B and the p orbital of the halide X, they make the antibonding hybrid state, which corresponds to the formations of the valence band maximum. Similarly, the non-bonding hybrid orbital, which is formed between the p orbital of the B metal and the X orbital of the X halide, they form the conduction band. And since the BX octahedra or PBX6 octahedra that can contribute to the band gap, by changing the halide, one can change the band gap. So that's why this material, it is very, very easy to tune the band gap by simply changing the compositions, the stoichiometry, and sometimes also the positions of the metal halides. Now, as I mentioned that this material is called a wonder material, there are several reasons for that. In our lab also, we have been involved with the applications of this metal halide perovskites for different optoelectronics application. For example, one of the primary applications of the metal halide perovskites is solar cells. This material shows a very large absorption cross sections, large absorption coefficient. They have a tunable band gap, and one can make it at a low temperature by a solution processable method. Remember, while processing the silicon, one needs a high temperature method. But here one can make this perovskite based solar cell at a room temperature without requiring the high temperature furnace. So that is also an advantage for this kind of materials in the applications of solar cells. Then there are light emitting diodes. Then there are lasers, different kind of nanocrystals, which can be used as a Bragg reflector or photonic crystal. Then there are transistors, detectors, and also various other kind of bioimaging probes, X-ray detectors, scintillation detector, nucleus detector, or gamma ray detector. Perovskite crystals has been used for different applications. Now, a typical perovskite solar cell device either is an NPN structure or a PNP structure. So what we mean by that, that usually a solar cell, we know that is consists of the two electrode. You have a FTO glass electrode, and then there is a cathode, which is an gold or silver or or any kind of metal electrode where the work functions matches properly. In between these two metal electrode, we usually put the perovskite layer. Now, to filter out a certain kind of charge carrier, we put the transport layer. Often we call as an electron transport layer or a hole transport layer. Now, this position of the electron transport layer and the hole transport layer can be interchanged. That can give to the inverted or non-inverted kind of perovskite solar cell structure. But whether it is inverted or non-inverted, the major part in this solar cell structure is the material perovskite. So therefore, it is very, very important to understand the morphological and photophysical properties of this material, both in polycrystalline state as well as in a single crystalline state. But what about the problems in the polycrystalline states is that there are lots of grain boundary exist in the polycrystalline film. For example, like, if you look at this ACM image of a polycrystalline perovskite film, you can see that there are lots of pinholes and cracks and grain boundary exist in the thin film. And as you know that the grain boundary contributes to the non-radiative charge carrier loss. So at the grain boundary, charge carrier electrons and hole recombine, and that contributes to the non-radiative loss. So we want to minimize this non-radiative loss while processing a good efficiency devices. In addition to this kind of perovskite bulk film is always susceptible to the different kind of environmental factors, for example, moisture or humidity, oxygen level, in addition to its intrinsic ion migration based instability. If the moisture or the humidity is exposed on the polycrystalline perovskite film for quite a long time, the grain boundary degradation increase. And also the perovskite 3D crystal structure disintegrates into 2D or one-dimensional crystal structures, so which is not a quite a desirable state. This kind of high trap state and defect density is sometimes detrimental for the device. Always, perovskite is usually known as a defect-tolerant materials, and there are lots of debate for the underlying mechanism behind its defect tolerance. Even a room temperature processable perovskite films shows a large number of traps and defects, and it needs a proper passivation technology to neutralize those trap states. And also, sometimes it is difficult to control the crystallinity, especially when we make a large area perovskite film, and to maintain the structural order in a large area perovskite film in this polycrystalline film. So this kind of disadvantages has opens up a challenge and opportunities for us to make a single crystalline perovskite based film and devices. Now, just like a silicon, we know that the single crystalline silicon is always better than their polycrystalline counterpart. Similarly, the single crystalline perovskite shows some of the amazing properties than its polycrystalline counterparts. For example, like, if you look at this ACM image where the polycrystalline perovskite and the single crystalline perovskite, they have been compared in the side by side. I should mention what is MaPbr3. Here this Ma actually is methyl ammonium organic cation, CH3NH3, and Pb is actually the lead and bromine is the halogen. So this is a standard perovskite crystal structure, the CH3NH3 lead halide, or this Ma-based lead crystal structure that is commonly utilized in different kind of solar cells and LED. Now one can replace this bromine either by chlorine or by iodine, and essentially we can change the band gap and their optical and electronic properties. Now if you look at this polycrystalline film and this single crystalline film, what you will see that there are almost no grain boundaries in this film. So in principle, all those passivation strategies, all those compositional engineering which have been developed so far for the polycrystalline film, that can essentially be removed by the single crystalline perovskite processing approach. So they really comes out with some of the very, very good properties. For example, they show a very high degree of crystallinity or high degree of order. And whenever we have a very high degree of order, that helps the charge transport. And this shows a very unique optical properties. Both the band gap and the band offset of this perovskite single crystal is quite different than the perovskite based polycrystalline films. There is no grain boundaries here, or very limited amount of the grain boundaries depending upon the processing protocol. And consequently, the number of the defect states and trap states is much less. And once the defect states and trap states is much less, then it is much easier to control the charge carrier dynamics even for a larger extent. Now, before going on the growth of the perovskite single crystal which we utilize in the lab, first I will give a very, very brief overview from our normal crystallography, and which is familiar to many of you. We know that there are two different kind of nucleation is there. One is called the homogeneous nucleation, and another is called the heterogeneous nucleation. So in a homogeneous nucleation, as we know, that there is a preferential nucleation site exists, and it occurs where there is no special objects exist inside our solvent phase to cause the nucleations. And this process is spontaneous and it happens randomly. Now you might ask, like, if a process is spontaneous or if it is not controlled thermodynamically, then how can we control the crystal growth? Yes, that is one of the problem in the homogeneous nucleations. And this animation shows, like, how the nucleations and the crystal growth process happens in a homogeneous nucleations process. We first start with the one nucleation site and it gradually build up and we got this large crystal size. Whereas for heterogeneous nucleations, it needs a preferential sites, either a phase boundary or a surface or some kind of impurities or dust particle. Now, since it needs a preferential site, the effective surface energy which is required for the nucleations will be much lower. And that actually decreases the free energy required for the nucleations and facilitates the nucleation in a much better way than the homogeneous nucleations. So that's why homogeneous and heterogeneous nucleations is much more common, or I will say that it's much more popular than the homogeneous nucleations. Here in this slide, like, I am showing a very small animations about the nucleation and the crystal growth so that it can give us a flavor of the idea, like if we want a small crystal and if we want a large crystal, how we can control the nucleation and growth. So if we start with our precursor material, and if the nucleation is very, very fast, but if the growth is still slow, we can get a small crystal. But if the nucleation is slow, then we can get a large crystal. So the idea behind this slide is that somehow we have to control the nucleations and the growth rate to get a large crystals. For the details of the thermodynamics and the process optimizations, you can look for our recent article in the JMRT, where we have seen that the perovskite single crystal growth, especially we have been using the lead-free perovskite single crystals. This lead-free perovskite single crystal growth, they completely depends upon the nucleation rates. And one can control the perovskite crystal size from a very small size to a very, very large size by controlling their thermodynamics parameter. For example, there are two standard methods which have been used to grow these perovskite single crystals are slow cooling method and inverse temperature crystallizations method. Now, I must mention that these are not the new methods. These methods have been also used by the inorganic chemists before for fabricating and synthesizing the inorganic single crystals. In the slow cooling method, first we increase the solubility of the perovskite precursor solution, then we allow them to saturate so that the excess amount of the materials inside the solutions, they get precipitated. And sometimes one can use an anti-solvent or other things. Now, both these methods, slow cooling method and the inverse temperature crystallizations method, have been commonly used for the perovskite single crystal growth. And if one can control the stoichiometry and the nucleation and the growth rate, one can even get a large perovskite single crystal as large as few millimeters or few inches. Now, not only these two methods, but in the literature, there are several other methods have been reported for the growth of the perovskite single crystal. For example, you know that not only the inverse temperature crystallizations method, but there are high temperatures methods is there, and there are solution processes method is there, and that techniques has been used for a plethora of materials. For example, not only we are using it for the lead-based materials, but if you change even lead to some other lead-free materials, or even like if you change the organic cation from Ma to some formalidium, or if you use an inorganic cation like cesium, or if you go to something like Ba or any other kind of small organic groups, or if you change the positions of the halide, one can grow the variety of perovskite single crystals by any either of this method, by changing the perovskites and by controlling their stoichiometry and the crystal growth rate. And it was very, very interesting to see that all of this method leads us to a very nice large perovskite single crystal. For example, you can see a millimeter size perovskite single crystal has been grown both for the iodine, bromine, as well as for the case of the chlorine. Now, if the crystal is as large as the 25 millimeter, then this single crystal can itself used as a nanoelectronics devices. One can actually deposit the electrodes on the top of these devices and can use it itself as a solar cell or a detector or any kind of lasers. So that is one of the advantages of growing the large perovskite single crystals in the solution phase. Now, as I mentioned earlier, they also show some typical optical properties. For example, like if you look their absorptions and their the band gap properties. So these perovskite single crystals not only show the stoichiometry dependence band gap, where their band offset changes from a lower to the higher depending upon the compositions, but also their PL intensity also get changed depending upon the changing of the iodine to bromine to chlorine. And there's one more interesting thing about their transient property is that if you compare the single crystal with a polycrystalline film, the lifetime is different. So the carrier lifetime is increased, and the total lifetime component, the part of the non-relative component has decreased, and the relative part of the lifetime has increased. So that means the VOC, which is actually the difference between the quasi-Fermi level, that also get increased in this kind of perovskite single crystal based silicon perovskite based single crystal solar cells. But one of the major problem with the perovskite single crystal is that to handling this perovskite single crystal to make effective device, especially the growth of the transport layer on this perovskite single crystal is very, very difficult, and one needs a lot of patience to make a perovskite single crystal based solar cells. And not only the optical properties, as you can show the electrical properties, which will be measured by the SCLC method, the high mobility is also seen both in this case of the FePV-Br3 and also in the case of the MePV-Br3, like single crystals in comparison to their polycrystalline film. Now, this perovskite single crystal has been utilized for detector, for FET, for making solar cells, for different kind of photoluminescence based devices, for example, sensors, then the visible light communications, X-ray scintillators, lasers, LEDs, and all kinds of optoelectronics devices. And very recently, there is a common interest among the world about making this perovskite single crystal based solar cells actually led to a very high efficiency as high as 21%. And there are some leading groups, especially from COST and UNI and JJD from China, they are actually contributing a good amount of research on the perovskite single crystal based solar cells research. But one of the major problem with the lead-based perovskite is the lead toxicity. Well, I mean, one can argue that although the lead has been commonly used in battery and many other optoelectronics devices, but it is true that the lead can leach to the environment and can give to the different kind of the health hazards. So the European Union standard says that anything less than 1000 ppm is actually allowed. But usually this lead-based perovskite solar cell, they use a lot of lead, and in case the lead comes out to the environment, although these solar cells are properly encapsulated, then they can be a huge environmental problem. And the second problem with the lead-based system is that their instability. Their intrinsic instability. The intrinsic instability means this kind of materials has an ionic and electronic properties, and when light falls on it, like their ionic and electronic parts get separated, and the ionic parts start moving in the crystal structure. And this is a phenomenon called ion migration. And this ion migration actually leads to a non-stable crystal structure in the perovskite. Moreover, there are different kind of environmental factors. For example, moisture or humidity and oxygen, they also contribute severely to the instability of the perovskite devices. So because of all of these concerns, scientific community, including us, we are very, very interested to grow some lead-free perovskite single crystal. And we are interested to see that if we replace the lead with some lead-free material, how the crystal structure, optical properties, and photophysical properties will change. In one of this attempt, we have been trying to replace the lead with the bismuth. Now, bismuth is isoelectronic with the lead. Bismuth 3+ has 6x2 lone pair structure, which is the same as lead 2+ structure. And also the effective ionic radius of the bismuth is 103 picometer, whereas for that case of the Pb2 ion is 119 picometer. So they are almost although slightly different but comparable. And electronegativity of the bismuth is close to the lead. For the case of the bismuth, it is 2.02, and for the case of the lead, it is 2.33. So because of all of this thing, bismuth, we thought that will be a suitable candidate for replacing the lead. And since it has already been proved by the different experiment that the inorganic cesium-based perovskite gives a very stable perovskite structure, so we also tried to replace the organic Ma and Fa cation by the cesium, which leads to the air stability, very high thermal stability, and also all other disadvantages associated with organic cations that can be minimized by using the cesium. So we have grown these perovskite single crystals lead-free perovskite single crystals by using the slow cooling method and also by the inverse temperature crystallizations method. In all of these cases, just like a lead-based perovskite systems, we have been successfully able to grow the 6 millimeter, 5 millimeter, or 3 millimeter, as you can see from this picture or the scale bar. They are very, very nicely defined and large perovskite single crystal. And this is one of the first report of the growing bismuth-based large perovskite single crystals. The X-ray diffraction pattern confirms their crystal structure. For example, like, if you compare between the cesium-based bismuth, chlorine, bromine, and iodine, there's a significant difference between the crystal structure. And we have done the DFT simulation to find out what is the reason behind the low current in this kind of crystal structure. Now, one can actually see that this perovskite XRD crystal structure analysis gives us this data that the cesium-based perovskite chlorine structure, that's an orthorhombic crystal structure, which is a centrosymmetric system, and the cesium-based bismuth bromine, that is a trigonal system, and the iodine system is a hexagonal system. So just by simply changing the chlorine, bromine, and iodine, we can change their crystal symmetry and as well as the space group. And since there a lot of properties like optical and electronic properties, even the spin dynamics can be controlled by the space group symmetry. So that's why this is a very, very important and handy information which tells us, like, that how we can change the different compositions of the lead-free perovskite single crystal to change their space group and also, like, their crystal structure. Now, the DFT simulation shows that this kind of CS3 BR-based systems, they are actually two-dimensional systems where they're in an individual single crystal, they are electronically capable, but when they're combined with each other, they don't talk very good fashion with the successive electronic structure. And that is one of the reasons for the low mobility of this lead-free perovskite single crystal. Now, we have seen that the absorption spectrum for the chlorine, bromine, and iodine typically shows the same pattern like an ideal crystal structure absorption pattern shows, and it gives a band gap of 2.81. Although the band gap is a little bit high in comparison to the lead-based single crystal, but by changing the stoichiometry of the chlorine, bromine, or chlorine and iodine, one can actually tune the band gap and brings it closer to the lead-based systems. The photoluminescence property shows that when excited at the absorption maxima, all of this perovskite, lead-free perovskite single crystal, either chlorine, bromine, or it is an iodine, this shows efflorescence properties. And we have taken also the Raman properties to see whether they are vibrational active, and all the Raman modes analysis shows that all of these three materials are quite vibrationally active. So this leads us to think about that if all these materials shows a good vibrational properties, and since the bismuth is there, so probably it will show a very strong electron-phonon coupling. And if there is a strong electron-phonon coupling is there, then one can probe this thing either by some kind of spin properties, by EPS spectroscopy, and it might be suitable for any spin-based devices. Now, before proceeding that, we also wanted to see that the thermal stability of these materials, and as you can see that the thermal stability of the material is quite large, it almost to 400 to 500 degrees Celsius. So that gives us an assurance that the thermal stability of the material is also very, very high. Now, I think I will have to finish it in another 4 to 5 minutes. So I will just quickly go to this, the two different things which I wanted to focus out here. One is the disorderness in this lead-free perovskite single crystal. One of the major concerns of the scientific community was there that, okay, the perovskite-based system has been proven to its best. But once I replace the lead with the lead-free perovskite, then there are lots of problems is coming. One of the major problem is the low charge carrier mobility and low charge carrier transport. Now, what is the reason behind that? We are interested to probe that what is the reason behind the low charge carrier mobility in this system. And what we found that if we compare the chlorine, bromine, and iodine, so the bromine, the Arbach energy calculation shows that where the Arbach energy is defined as the 1/dd of the log absorptions. So it shows the disorderness of the systems. And this Arbach energy calculation shows us that bromine-based system has a very large disorderness in comparison to the iodine and chlorine-based systems. And because of that, the charge carrier mobility of the bromine-based system is less than the chlorine and iodine-based system for this lead-free perovskite single crystals. Now, even the EPR spectroscopy data further confirms the observation which have been confirmed in the SCLC mobility and also by this Arbach disorderness. We have also done the EPS spectroscopy, the temperature-dependent EPS spectroscopy, which shows the the variations of the Lambda G factor for the three different perovskite. And what we have seen that in the case of the bismuth, there's a very strong electron spin coupling, like electron-phonon coupling is observed in comparison to the iodine and chlorine-based systems. And this strong electron-phonon coupling has been even calculated to find out the splitting in the magnetic energy level. And as you can see from this energy, here the EPS spectrum as a function of the temperature has been done for the different magnetic field and for the different perovskite single crystal. For example, if we change to the chlorine, bromine, and iodine, we can see a distinct difference in their Lambda G factor value and also their peak distributions value, which actually tells us there's a different orders of the spin orbit coupling exist in this system, and a calculation of the spin orbit coupling constant gives that the bismuth shows a very large amount of the spin orbit coupling constant, and which is almost same like those material which have been used for the spintronic material application. So that emerges this fact that this bismuth-based lead-free perovskite single crystal can be an ideal candidate for spintronic devices. I'll complete my talk with a very, very unusual phenomena we have been observed in the negative photoconductivity in the perovskite single crystal. We just have been submitted this paper. It is under consideration right now. And what we have seen, a very, very amazing phenomena, that this lead-free perovskite single crystal shows a negative photoconductivity. Now, negative photoconductivity has been reported in the literature previously also. But in the lead-free based systems, this is the first report of a negative photoconductivity. Now, what do we mean by the negative photoconductivity is that, like, for example, you can see that the current IV curve here, in the dark, it shows by the black line. But when you put the light, the current decreases. Okay. And now if I expose the light for the more and more time, let's say for 15 minutes, then it decreases more. So that means the current decrease as I expose the light. And then if I switch up the light, after 60 minutes or after 150 minutes, gradually the current recovers. And finally, at the end of 180 minutes, all that currents which have been depleted, that get recovered. So that means there is a trend between the current and time. Initially, the current degrades, and then finally it recovers. Now, what is the reason behind that? Usually what we'll expect that, like when there is a dark condition is there, that the solar cell is working, or any kind of material, like, with the two electrode systems, that will work as a diode system. So the minority carrier is mainly contribute to the charge carrier. Now, when you put the light, you will expect that there is more charge carrier has been generated. So the I should be increasing, but instead of that, I is decreasing. But even another interesting fact is that even if I switch off the light, so then those decrease can be recovered. That means whatever the current has been depleted, that comes back to the original value. So this is quite bizarre, and that can be utilized for making ultra sensitive photodetector, because a very, very small amount of current can give a change in the signal. Now, since this paper is under consideration, we have not shown the results here. We are further interested to see that, what is the reason behind this negative photoconductivity, and what we found that in the presence of the light, there is a metastable trash state formed in these systems. And this metastable trash state, that actually trap those photogenerated charge carrier. And once we switch off the light, the metastable trash state, since it is not very highly energetic, they release those charge carriers and they can come back at the conduction band. Both the wavelength dependent transient absorption spectroscopy, density functional theory, and temperature dependent study confirms that there is a light induced metastable trash state has been formed in these systems. And this is not only for the chlorine, we observe the similar system in the case of the bromine. So this is quite peculiar phenomena, and this leads to the fact that this kind of single crystals have a very, very high promise of making ultra sensitive detector. Now there are challenges, there are also some promises there. So I discussed that the large single crystal to single crystalline films with the control thickness can be formed by this perovskite single crystal growth method. And the development of the strategies to prevent the self-doping in the single crystal has to be optimized. And development of the proper electron transport layer and hole transport layer and the passivation strategies, even the surface traps in the single crystals, that has to be developed still yet. And dimensionality enhancement in the lead-free perovskite single crystal is one of the challenge. And the last and the final challenge is that to fabricating a good devices out of this perovskite single crystal materials, because as I mentioned, that handling these perovskite single crystal materials is quite challenging and they can lead to different kind of damage, and also different kind of leaky current in the devices. So that's why the research is ongoing, but this material has a very, very high promise. And even if somebody can make a lead-free perovskite single crystal, like those days are not very far, we'll be able to make a completely lead-free perovskite based all sorts of optoelectronics device. With this, I complete, and I like to acknowledge all my funding agencies, like including DST and the CSIR and Ministry of Information and Electronics and Information Technology and MNRE. And this is my solar cell research groups. Most of the work I presented here today, that was done by these PhD students from all of these people. And finally, I like to thank you for your presence, and I pray all of you to be safe and healthy.